Okay. Apparently I got a bunch of messages.
I spammed you. I apologize.
That was all this morning.
Yes.
Boom, boom, boom. All right, well. I was meeting with a student during that time. I apologize.
No, it's
Well,
fine.
prospective student. Okay, let's see where we at. Exam 1 is due today. Is anybody gonna have trouble getting that done? Are we good to go? Okay, if you do have any questions or concerns about exam 1, please make sure that you contact me today so we can take care of that. We are continuing on in chapter 5 here. We just started chapter 5 and we got through chapter 5.1, where we discussed forces in general. And now we're moving on to Newton's laws about forces. Newton's laws in general are quite misunderstood. Many scientists even misunderstand them, in my opinion. But it's erroneously thought that laws are somehow things that we've proven to be correct or something. And that is not the case at all. In fact, laws are unprovable. Laws are things that scientists discover / formulate, I guess is a good way to say it, as they're observing nature around them. In Newton's case, he was observing, he was looking at the data, he was looking at the observations of many other scientists, including Johannes Kepler and Tycho Brahe and Galileo Galilei and many others, many great scientists that came before him and at the same time as him. And he was also looking at his own experiments, and he was trying to look for patterns in the behavior of things in the universe. And most of these people that he was studying for, like Brahe and Copernicus and others, they were studying mostly the heavens. They were studying the motion of the planets. It was really what they were studying. And they were taking a lot of data. They were writing down a lot of things that they observed. And as Newton was looking at these recordings of these records and doing his own experiments, he was looking for patterns, things that always happened the same way, or things that fell into the same kind of category of behavior, or whatever. And one of the first things he noticed was something about movement of massive objects. And this is where his first law of motion comes into effect. Newton's first law says that a body remains at rest, or if it's in motion, it remains in motion to constant velocity unless it's acted on by net external force. So essentially what Newton observed is that things that are doing whatever they're doing out there tend to keep doing it unless something changes what they're doing, right? And if things are just sitting there, they just continue to sit there unless something comes along and forces them out of that position, right? And when he means net external force, what that means is a net force is an overall force. So if you add all the forces together acting on an object and you have some number that's not zero, then that's a net force. Because forces are vectors like velocities and displacements and other things, they can add together to be zero quite easily. So a net force would imply that there's some leftover force that's not being canceled out. And an external force means that it's something that is not the object of interest acting on it. So if you're looking at the moon, an external force would have to be something that's acting on the moon that's not the moon, right? Like the Earth's gravity acts on the moon. And the Earth's gravity doesn't come from the moon, it comes from the Earth. The sun's gravity acts on the moon, and the sun's gravity comes from the sun, not from the moon. So those are external forces. But the moon's own gravity is an internal force. The moon's own gravity is responsible for shaping the moon in the shape of a sphere-ish thing. That's why planets are generally spherical, is because gravity pulls in all directions towards the center of the mass. And that eventually results in something that is pulled into a spherical shape. But that's an internal force, not an external force. So the moon's gravity doesn't affect its motion. The Earth's gravity doesn't affect its motion. Only the sun's gravity affects the Earth's motion, and the moon's gravity affects the Earth's motion, but not its own internal forces. And this may seem contradictory to maybe some of your experiences. For example, a human being has the ability to move. You move your arms and your legs, and you can actually, some humans think that means that they can use their internal forces, the forces that cause their arms and legs to move themselves without any external forces, but it's not true. When you're sitting in a chair, for example, and you move your body to scoot the chair forward, you're not using internal forces to move the chair forward. As you move your body, that creates another force, which is an external force to move the chair forward. And we'll learn more about that when we get to Newton's third law. So Newton's first law of motion is that things are either at rest or they're in motion. And if they're going to change that motion or that at restness, it has to be an external force that causes that change. Now, what about things that are moving in circles? Well, things that are moving in circles are constantly changing their movement. So they only fall under this law in the fact that so let's say we have a moon orbiting the Earth, the moon's orbiting the Earth, and you say, well, will the moon continue to orbit the Earth as long as no external force changes its movement? Well, an external force is always changing its movement. It's already changing. It changes every time the moon turns in its orbit, which is constant, right? So if you turned off the Earth's gravity, what would happen to the moon? Yeah, it would. That's a good explanation. If you turned off the gravity of the Earth, then the moon would only be affected by the gravity of the sun, as far as nearby objects, and maybe to some extent the gravity of Mars, which is the next, the most powerful gravity that's affecting the moon. Besides the sun and the Earth, but it essentially would stop orbiting the Earth, and it would move in a straight line relative to where the Earth was, but it would still orbit the sun, so it would still be in that orbit, right? So essentially, the Earth is the thing that's turning it all the time, and so it was the external force that was causing that change. Did you have a question, Danny?
No, I wasn't asking something. I was confused about the order of planets. Are like zero, like gravity of Mars, affecting the rest of Jupiter.
Yeah, Jupiter's far enough away and low mass enough that it's probably not affecting it as much as Mars, I would guess. I don't really know if that's true, but they're minimal effects anyway. The orbit of planets in the solar system is very complex because all of the gravities from all of the objects in the solar system affect everything else to some degree or another, larger or smaller degree. And that effect comes from mass and distance, and we'll learn more about that later. But yeah, it's a pretty complex situation. In fact, if you map out the movement of the Earth around the sun, it looks nothing like a circle or even an ellipse. It actually kind of looks like a pearl necklace or something. It actually the Earth is rotating around the moon like the moon is rotating around the Earth. It's a much smaller rotation. And as it rotates around the moon and then rotates around the sun, if you map out the rotation of the Earth, it looks like a very fine beaded necklace instead of some kind of perfect line circle or ellipse. So it's very complicated. And in fact, in more extreme situations, you have more complications. For example, Pluto's orbit is really greatly affected by the next nearest planet, which is Neptune, right? Is it Neptune or Uranus? I can never
One of
remember
them
which
I
one.
know for a fact that one of them is stealing a small amount of mass every time they go by each other, so Pluto's definitely shrinking.
Yeah, so yeah, Neptune is, if it's Neptune or if it's Uranus, I don't remember which one. But whatever the planet is that's closer out to Pluto, Pluto's orbit actually comes closer than that planet's orbit for part of its year. Because when they get close together, that planet attracts Pluto more than the sun does, slightly. And so it actually pulls it in close, and that's why Pluto's orbit is so wonky and weird. And that's also why astronomers classified it as a planetoid and rather than a planet, and caused all the controversy. Is Pluto a planet? I'm like, whatever, who cares? What, it doesn't matter what you call it. It's still the same thing it was before. It'll still be the same thing later. But anyway, it's very interesting. And Pluto's moon is actually almost as big as Pluto itself. So its orbits or its behavior is really strange. But Newton certainly observed this pattern. And he had no explanation for it. There is no explanation for it. There's really just an observation. And that's what laws are. Laws are things that we observe that always happen, patterns we observe in the universe that always are the same. There's always things that always follow the same pattern, the same behavior. And we can describe it, but we can't explain it. There's no explanation why it happens. We do know some things about it as we've observed it over the hundreds of years. We do know that mass is directly related to inertia, to this idea of Newton's first law, which is what we call the law of inertia sometimes. The word inertia comes from Latin or Greek, I don't remember which one, and it means to not change. So it means unchanging. So the law of inertia means that the movement of objects or the non-movement of objects doesn't change unless you force them to change. And this inertia is directly related to mass. We know that objects that have more mass, it's harder to change what they're doing. They continue to do what they're doing more so than things with less mass. And so mass, the measuring of mass is a direct measurement of the amount of inertia that something has, right? And I mean, it's really interesting because there is such a thing as rotational inertia. So an object that has mass that is rotating about its center of mass, for example, like the Earth, will continue to rotate around the center of mass. It doesn't require any force to keep it rotating. It will continue to rotate around its center of mass. And the Earth has been rotating around its center of mass for billions of years without hardly any change to it. Even though many of things have tried to change it, many things have collided with the Earth. The moon is constantly trying to change things about the Earth as it, exists out there. All the movement on the Earth of things that are not the Earth, like humans and animals and everything. None of these things have had a significant effect on the rotation of the Earth because the Earth is so incredibly massive. The only thing that may have had an effect on the rotation of the Earth was actually the formation of the moon itself, possibly, because one of the theories about how the moon was created was that a huge heavenly body from the solar system, like probably the size of the moon or so, maybe collided with the Earth at some point and broke off part of the Earth and created the moon, essentially, so that there were two objects orbiting each other, and eventually they coalesced into the moon and the Earth. And that's one theory about how the moon was created. And that would have definitely affected the rotation of the Earth. So it would have either created more rotation or less rotation, depending on how it happened, or a different kind of rotation. But regardless, it will just keep doing this until something else big enough comes along with enough mass to really change it. So Newton's first law, things remain at rest, or if in motion, they remain at motion with a constant velocity unless acted on by the net external force. And that constant velocity includes both the magnitude of the velocity or the speed and the direction. So it's a linear thing. Here you have an example of a hockey puck and a hockey stick, right? So the hockey puck's just sitting there. And it's going to remain sitting there until the hockey stick comes along and applies a force to it. It's an external force from an external object, and then the hockey puck now is doing something different. Very simple. Here we see, if you've ever played air hockey, you know that when you put the hockey puck on the table, oftentimes it starts to just move around randomly. And you think, well, doesn't that disobey this law of motion? Well, no, because air hockey tables have little holes in the table that air is coming out of. And that air has mass. That mass is pushing on the air hockey puck. And it's not pushing on it perfectly equally on both sides so that the forces cancel out. Sometimes it's pushing more on one side than the other. Sometimes the hockey puck is lined up over the hole, kind of wrong, kind of unbalanced. And gravity is pulling down on the hockey puck. And if you're pushing up on one side and pulling down on another side, you're going to cause things to tilt and to rotate, and you're going to cause all kinds of imbalances of force, and the hockey puck will move slightly. Because it's not a lot of force, it's just a little bit. So that happens. And that's also why air hockey is fun. Air hockey wouldn't be fun without the air, because the hockey puck is essentially floating on the air, which gives it a very low friction, which allows you to hit the hockey puck pretty quickly. It's also why hockey is played on ice, because ice and rubber have a very low friction between them, and the hockey puck's made of rubber, right? So you get a very fast moving puck over the surface. That's the point. Now, this idea of inertia brings up the idea of inertial reference frames. When we're talking about inertia and we're talking about things sitting still and things moving, we have to decide what our observational frame is, right? Because if we're saying, oh, well, we're on a hockey rink and the puck is sitting on the hockey rink and sitting still, is it really? That whole hockey rink is on the earth, which is certainly not sitting still, right? The earth is rotating around its axis. It's orbiting around the sun. The sun is moving through the solar system, moving relative to other stars nearby with the entire solar system. And we're actually in an arm of a galaxy that's rotating, and the galaxy that we live in, the Milky Way galaxy, is actually moving. There's all kinds of movement going on, but we don't observe that movement because our reference frame is the reference frame of the earth. We think of the earth as sitting still, but we think of North Platte as a place that is always in the same place, but it's not. But we think of it that way because we think in two dimensions, and we think of the earth as not a sphere moving through space, but as a flat thing that we live on, right? We're all flat earthers here. There is no such thing. I mean, so few people on earth actually believe the earth is actually a sphere in the way that they think and the way that they live their lives, that you could probably count them on one hand. Everybody's a flat earther. We all believe the earth is flat. That's how we behave. That's how we measure things. That's how we do our math. That's how we do our engineering. We behave as if the earth is not moving. And for us, in the inertial reference frame that we're in, it works just fine. The true definition of an inertial reference frame is an observational frame that is moving at a constant velocity relative to any other inertial frame. It turns out that there is no such thing as an inertial reference frame. We're defining this so that we can make some assumptions and make the math easier. But it turns out that nothing in the universe is not accelerating. Everything is accelerating in the universe relative to something else out there. And that's just a fact. In fact, that is such a general and universal fact of nature that everything is accelerating compared to something else in the universe, that Einstein, when he put together his general theory of relativity, he actually made that the basis for the general theory of relativity, that there's no difference between accelerating frames and gravity. because gravity is a force that reaches out into the universe and causes things to accelerate. But how do you know if you're accelerating due to gravity or you're accelerating due to some other thing? You don't know. There's no way to tell the difference. And that's the basis of his general theory of relativity, is that we don't actually know the difference between acceleration due to gravity and acceleration due to something else. And so we just have to call it all acceleration. It's just acceleration. Anyway, so the inertial reference frame, and we'll reference this every once in a while, no pun intended, but we won't take great pains to talk about it in detail. Now, equilibrium, Newton's first law. What is equilibrium? Well, equilibrium equilibrium literally means the equality of forces, or the equality of actions, I guess, suppose you could say. Doesn't have to be forces, but equilibrium in physics we generally think of as all the forces adding together to be zero on an object, so that there is no force, no net force on the object, no net external force. And what that means is that you're not going to change the motion of the object. So equilibrium is what happens when equilibrium is a condition that shows Newton's first law is correct. Yes.
So is it fair to say from that description that nothing in circular or orbital motion is equilibrium, because there's always the centripetal acceleration?
Yes. So if you're familiar with if you're familiar with the ideas of centripetal acceleration, then you can immediately jump to the conclusion that something that is turning or rotating, something that is turning or orbiting something else, or traveling in some kind of curve, turning in any way really, cannot be in equilibrium, because that requires an acceleration, and equilibrium requires the acceleration to be zero. It also requires that forces equal zero, external forces, right? So yes, you can definitely make that conclusion. That's actually a conclusion that Newton came to. And that's actually how he figured out how the planets travel through space. Because he said there has to be something turning them. Something has to be turning them. And he said, well, wait a second. What if the same thing that causes us to stick to the earth, this is where the idea of the apple falling out of the tree came from. What Einstein said is, what if the same force that causes the apple to fall out of the tree towards the center of the earth is the same thing that causes the moon to orbit the earth? What's the difference? The difference is that the apple, as the earth is rotating, the apple is rotating with the earth at the same speed the earth is rotating. So when the apple drops from the tree, it just falls straight towards the earth from our point of view. If you watched the apple fall in space and it deleted the earth, so that you couldn't see that the earth was there, the apple would actually fall in a kind of a curve, because it would also be moving with the earth's rotation, which is fairly fast, much faster than it would be moving towards the earth. So the apple is actually moving sideways more than it is down. If you ignore the fact that it's moving with the earth, you just say, oh, it's just moving through space. It would actually be moving faster sideways than towards the center of the earth. It's a very similar thing to dropping an apple from the top of a moving ship. When a ship is moving, let's draw a picture of this really quick. If you have a sailboat moving along the water like this, and you've got the sail here, and you go up to the top of the mast and you drop an apple. If you're on the ship and you watch that apple fall, it looks like it's just falling down the mast straight down. But if you erase the ship and you just look at the apple, and you're looking at the waves down here. So you have these waves down here, and you're watching the apple fall relative to the waves. The apple falls like this because the ship has moved forward while the apple is falling, right? But if you're sitting on the ship and you're not paying attention to the waves underneath it, and you're just watching the apple, it just comes straight down into your lap as you sit at the bottom of the mast. But it actually falls forward because the ship is moving forward, right? It's the same with the earth. The apple is on a tree that is moving with the earth. And so the apple is actually falling in this curved path as the earth rotates around its axis, right? And that's the difference between the apple and the moon. The moon is not orbiting with the earth. The earth, as the earth goes around, so if this is the earth and it's rotating around at a speed represented by this arrow, the moon is actually rotating faster than that around the earth, a much bigger arrow. It's moving much faster than the surface of the earth is rotating. And that's why sometimes we can see the moon at night and sometimes we can't, because sometimes the moon is up there at night and sometimes it's up in the sky during our daytime, because the earth's rotating differently than the moon is rotating around the earth, right? But this is the reason that it stays up there. The reason the moon stays up there is as it falls towards the earth, because the moon is falling towards the earth, for sure. But as it falls towards the earth, it's also moving forward. So it's actually moving over the horizon as it falls. So it's actually falling around the earth. Instead of falling towards the earth, it actually falls around the earth. It falls over the horizon instead of falling towards the actual earth, right? And you could do this with a golf ball, theoretically. If you hit a golf ball hard enough so that it is accelerating, so that it's going so fast that when it falls 1 inch, it's actually gone 1 inch over the horizon, it would be in orbit. It would stay in orbit. So you can hit a golf ball fast enough, theoretically, to be in orbit, a couple feet off the ground, or 1 inch off the ground if you're hitting it off an inch high tee. But you'd have to hit it so fast. It'd have to be incredibly fast. So incredibly fast. It's insane to think how fast it couldn't be done practically. But that's what we do when we send spaceships into orbit. We don't just fly them straight up. If you've ever watched a spaceship launch, it doesn't just fly straight up in space and then it's in orbit. That's not how it happens. How it happens is you fly it straight up for a little bit and then it turns sideways. You can actually see this happen with spaceships. They actually pitch over and start shooting sideways because they have to be going fast enough so that when they fall over the edge of the earth. They fall over the horizon so that they're falling with the curvature. As the curvature drops off by a foot, they fall a foot. And as the curvature drops off by another foot, they fall another foot. So they're falling around the earth. That's what orbit is. So all of these things were things that Newton was thinking about as he observed his experiments and as he observed the data from other people's experiments, as he looked at all the information that people had gathered. And he said, you know what? I think that the planets are held in orbit around the sun for the same reason, by the same force that causes apples to fall from trees. And he equated those two. It hadn't been done before. Nobody knew why before. People had put together enough information to figure it out. They just hadn't put two and two together. Excuse me. And here we have a very common misconception about this as well. We have two cars here moving. One of them's not moving, actually has a velocity of 0. And that one has a net force of 0. But here we have a car moving at a constant velocity of 50 kilometers per hour. What's the net force on this car? You can answer this question from Newton's first law. What does Newton's first law say? Not quite. That's not quite what it says. Go ahead.
Wouldn't it be the net force is 0 because it doesn't show acceleration, it just shows the velocities immediately 50 kilometers per hour. So
yeah, so it's a constant velocity because I said that, right? And that in part B here, down here in the caption says that it is a constant velocity. If you have if something is either at rest, which is part A, or it's at a constant velocity, it's not changing its speed, it's not changing its direction. If it's in either one of those situations, then the last part of what you said is true. Then the sum of all the forces, or the net force, is 0, right? So things will remain at either a zero or constant velocity if the net force is zero. And if the net force isn't zero, then that's when you get something that's changing. It's either speeding up, slowing down, or turning, right? That's what happens. And we're not seeing that in either of these situations. Most students of physics kind of struggle with this second one because they think, well, it's moving. There must be something that's keeping it moving, because that's our experience. We have this experience in our life that says, if you're driving a car, you have to push on the gas pedal a little bit to keep it moving, right? When you start your car and you start moving, do you have to push on the gas pedal more to get it started or less than when you're just keeping it going? It actually doesn't really depend on how you drive. This is actually something that is absolutely true across all situations. If everything else is equal, if the car is equal and everything else. When you start going in a car, you actually have to push on the gas pedal a little bit more to get it going. And to get it up to speed, you have to push on it a little bit more. But once you're up to speed, what we all do with our foot, even if we don't realize it, is we all relax our foot a little bit. It's something we learned back when we were learning how to drive a car. You get up to 25, and then once you're at 25, you can't just take your foot off the gas and then just keep rolling. You have to keep it on a little bit. Why? And then just a little bit. It's not as much as to getting up to speed, but just a little bit to keep the car going. Why? Friction. There's all kinds of things trying to stop the car. There's all kinds of external forces. There's air pushing on the car. The ground is pushing on the tires. There's friction in all the bearings and all the moving parts of the car, right? All those things are forces that are pushing backwards on the car. They're external forces trying to slow the car down. So you have to keep the car going by putting a little bit of forward motion from the engine into the wheels, just by putting a little bit of force on that gas pedal. Not much, just a little bit to keep it going, right? So what is the net force in that situation? Well, the net force in that situation is you have all, so we're going at this constant speed now. We've just got our foot on the pedal a little bit. We've got a bunch of frictions pushing backwards on the car. We have air friction, we'll call that one A. We have ground friction, we'll call that one G. We have friction in our bearings as the wheels rotate, we'll call that bearings friction, we'll call that B, whatever. All these different frictions that are trying to slow the car down, but we have a little bit of force from our engine just from pushing on the car, just pushing on the pedal a little bit of force that is pushing backwards on the ground, and the ground pushes us forward. We'll learn more about that later. That overcomes all of these. So this friction, this force back here is equal to the sum of all of these forces, which are pushing the other way. So they all cancel out in the end. So the total force on this, the total external force, is zero. If you actually do the calculations, it is absolutely zero if it's at a constant velocity. It's not an estimate. It's an exact number. It's an exact thing according to what we understand about forces. So if it is not moving at all, at zero, it has a velocity of zero, then net force is zero. If the movement is a velocity that's not changing, a constant velocity, it's not speeding up, not slowing down, not turning, then the net force is also zero. Those are the two situations for Newton's first law. And both of these situations are what we call equilibrium situations, where the forces add to zero. There are other forces involved here that we haven't talked about. There's the force of gravity pulling this car downward towards the center of the earth. We call that the weight of the car. There's also a force of the earth. The surface of the earth is pushing upward on the wheels. It turns out that those forces cancel each other out. The weight downward and the surface force upward cancel each other out because the car is not moving in that direction. It's just sitting there, right? So there are other forces involved, but they all cancel out as well. And there's equilibrium. This type of equilibrium where the car is not moving at all, velocity is zero, we call static equilibrium. And if you go into civil engineering or mechanical engineering, you'll take an entire class on static equilibrium. It's called statics. And then this one is called dynamic equilibrium, where it's moving at a constant velocity, but the forces still add to zero. And if you're going into mechanical or civil engineering, you will take an entire class that's just on this, and it's called dynamics. They have very different things that you learn about each of those situations. So. Examples of things that you'll learn about in static engineering, statics. It's called mechanics statics actually, but examples of things you'll learn about in that are, you'll learn about how bridges are built, for example. Bridges are designed to handle a lot of forces, but not move, right? And the examples of things that you'll learn in dynamics are things like, cranes or bearings in cars or other things like this, where the forces are designed to move things, and things are designed to be moving with them. But they're still, the forces still add to zero. All right, so yeah. A really good way to test this, to test Newton's first law, is actually to take your two cars, your two IOLAB cars, and hook them together with their force transducers. If you hook the two cars together with their force transducers, and then you pull on them just gently so that they're not accelerating, they're just sitting there and you're just pulling on them, and then measure the forces on each of those transducers. It will be the exact same force if they're calibrated correctly. It'll be the exact same force on each transducer, but obviously they're in opposite directions because you're pulling one way with one and you're pulling the other way with the other. So those forces will add to absolute zero, and this thing is not accelerating. And then you do the same thing and you move them at a constant velocity, and it'll give you the same exact thing if you can keep them at that constant force the whole time. But even if you change the force, if you change the force on one, the other one will change the same amount exactly. You can just pull harder with this one, and this one will change the same amount as this one does, and it will still be adding to zero. So it's a good way to test that. And I just came up with that just now. I've been trying to figure out a good way to do an experiment with Newton's first law, but now I'm going to have to write a lab for that. We'll have a new IO lab for Newton's first law. Anyway, incidentally, it's also a good experiment for Newton's third law, which I have thought of before, but it's couched somewhat differently. So now we go to Newton's second law. Newton's second law is the law that, excuse me, is probably the most famous for its formula. I would say that Newton's first and third laws are very famous colloquially because people have made phrases about them that people think apply in everyday life. So for Newton's first law, people say an object at rest tends to remain at rest unless it's acted on by an external force or something like this, right? And that's an incomplete colloquial version of Newton's first law. But people have kind of, they use that to talk about the unmovable object, versus the unstoppable force or something. They do this in movies and books and things like this, pop culture all the time. But their understanding of the law is incomplete because it also works for moving objects, right? So it's kind of weird that they've done that. Newton's third law also has many colloquial phrases that people apply in everyday life. And their understanding is equally unsophisticated with that, unfortunately, because it becomes less scientific when you colloquialize something, make it kind of popular. But anyway, Newton's second law is also famous in its own way, but it's probably the most scientifically famous for its formula because it actually has an equation associated with it. And this equation has to do with the relationship between force and acceleration. This is another thing that Einstein was able to figure out, and he figured this out by doing many experiments with rolling balls down hills and things like this, and other similar situations, sliding things down ramps. And what he discovered is that the relationship between force and acceleration has to do with mass. He discovered that the more mass that you have, if you give it a specific amount of force, if you give an object a specific amount of force, the more mass that it has, the less acceleration it experiences. And the less mass it has, the more acceleration it experiences. Or you can think of it in terms of, think of it in terms of the acceleration or the force, whatever. You can actually rearrange this in many different ways. There are many different ways to think of it. But the formula comes out to be a very simple formula. Force equals mass times acceleration, which they write here somewhere. Where do they write it? Here we go. Here they write it, acceleration is proportional to the force. So if you apply more force, you get more acceleration if the mass remains the same. So that's a different way of thinking of it in terms of acceleration. If you have more mass, you get, well, sorry, if you have a particular amount of mass, you have something that's 1 kilogram of mass, for example. 1 kilogram is about, a small book, a small textbook, maybe, is 1 kilogram. And if you have this textbook and you apply a certain amount of force to it, pounds is one way of measuring force. So if you apply 5 pounds of force to this textbook, it might accelerate maybe 1 meter per second squared or something like this. But if you apply 20 pounds of force, did I say 10 pounds the first time? I don't remember. If you apply twice as much force to it, then it will accelerate twice as much for the same amount of mass. So it's directly proportional to the force, the acceleration. But the acceleration is inversely proportional to the mass. So if you increase the mass for the same amount of force, you get less acceleration. So there's an inverse proportionality with mass and a direct proportionality with force. And that means that, that we're going to either have to say that acceleration equals force divided by mass, or we're going to have to say force equals mass times acceleration, one or the other. And it doesn't really matter which way you choose. Here's that inverse proportionality with mass. And here's an example of that that's pretty obvious. If you give 10 pounds of force to a basketball, you're going to cause the basketball to fly out of your hands. But if you give 10 pounds of force to a car, you're barely going to accelerate the car at all, because the car has so much more mass. Right? That's very true. Those two situations. So we write it the first way as acceleration equals force over mass. And it turns out that since acceleration is a vector quantity, then the other side of the equation needs to also be a vector quantity. But we know that mass is not a vector quantity. Mass doesn't care about direction. It's just an amount of something. So the force has to be the thing that is vector. So force is definitely a vector. Force has magnitude and direction. And this is Newton's second law. It's also very often written like this: force equals mass times acceleration. Doesn't really matter which way you write it. There's also another way to write it, which is the way that Einstein wrote it, which involves momentum, which we haven't learned about yet. So we'll learn about that later. It also involves more calculus. This one obviously might involve calculus if you have continuous forces rather than discrete forces, because whenever you go from a discrete to a continuous situation, you always go from summation to integral, but we're not going to deal with that here. So in either case, though, it does matter that you add the forces together. You have to take all of the net external force on the object and add them, all the net external forces together, to make one total vector for the total amount of force. And then this equation becomes true, or this equation becomes true, either way. In one dimension, it's really easy, because in one dimension, you don't have to worry about the vector quality of your forces. You just have to worry about the sign, and that's enough. And so you get an equation like this. And you can also think about the magnitude of the force, the net force, and the magnitude of the acceleration, and use this equation for any dimensional situation. But in one dimension, it simplifies down to just a very simple scalar equation. So let's look at an example here. Actually, let's go back to the before. Here we have a bunch of examples of forces. Here's some people pushing a car. Each person exerts a force. There's the weight of the car. There's the force of the ground on the car, pushing upward on the car to keep it from falling to the earth. There's friction, right? Whenever we're dealing with lots of forces on an object, we usually draw a free body diagram to organize the forces. And a free body diagram simplifies the object of interest usually down to a point or a very simple shape. And then we draw all the forces starting at that point and going away from it. So these two forces pushing from behind are now going from the point to the right in front of the car. The friction, which is pushing from the front towards the back of the car, is now over here. And the weight is pulling down this, what we call the normal force, which is the force from the ground pushing up. The normal force is always a contact force between two objects in contact with each other. It's pointing upward here. And the free body diagram helps us to organize our forces and helps us to see what's going on at a glance. And you usually want to draw your forces proportionally. So the weight and the normal force should be equal and opposite because there's no acceleration in the y direction or the up and down direction. So they should be the same amount pointing in opposite directions because they need to cancel each other out because there can't be any acceleration now. According to Newton's law, if there's no acceleration, there's no force, so the forces have to add to zero. But in the horizontal direction, they're actually getting movement. They actually have acceleration from this. So the fact that they have acceleration tells us that these are going to be unbalanced in the horizontal direction. The force 2 and the force 1 pushing are added to the friction is going to equal an overall amount of force in the right-hand direction. Here's another situation with a car on a tow truck, free body diagram. Now there's only one thing pulling the car forward, and that's the tow truck. There's still friction involved. There's still weight of the car, still the normal force, but only one forward pulling force. Here's a situation where we have a man pushing a lawnmower. Now, the interesting thing about pushing objects is that when you push on an object to make it accelerate, the force will actually transmit itself through the object, through the physical object. So his pushing on this handle actually creates a force that acts down the handle like this. And if you've ever mowed a lawn, you know that to be true. If you've ever mowed a lawn, you know that when you're pushing the lawnmower forward, it actually pushes the lawnmower slightly down into the ground. There's some force that's pushing it downward. You actually get a shorter lawn when you're pushing the lawnmower rather than just sitting the lawnmower there and turning it on and letting it sit there. It'll actually push into the lawn a little bit, cut it a little bit shorter. However, they've not told us what the force is on the lawnmower handle or in the lawnmower handle. They've just told us the net force. So they've added all the forces through the handle. They've added the frictional force. They've added all the forces together on this lawnmower, the weight of it, the normal force pushing up on it from the Earth's surface. They've added them all together for us, and they've told us the net force is this. And the net force should always point in the direction of the acceleration of the object. In this case, we know that lawnmowers accelerate horizontally when you push them. So that makes sense that the net force is horizontal. And then they give us some numbers. Net external force is about 51 newtons, which is about 11 pounds of force parallel to the ground. Mass of the mower is 24 kilograms. What is its acceleration? Well, Newton's law says that acceleration equals force over mass in one dimension. And this is in one dimension. Everything's horizontal. They've given us the net force horizontally. We're calculating the acceleration horizontally. 51 newtons divided by 24 kilograms gives us an acceleration of 2.1 meters per second squared. Now that's a reasonable amount of acceleration as long as it doesn't happen for too long of a time, right? 2.1 meters squared is about a little bit more than 6 feet per second squared. So after 1 second, this lawnmower will be moving 6 feet after every second. After 2 seconds, this lawnmower will be moving 12 feet every second. And 12 feet is on the edge of mowing a lawn while you're running, 12 feet per second, okay? So you probably are not going to be moving, you're probably not going to be mowing at 12 feet per second. So you would imagine that this acceleration would only happen for 1 to 2 seconds, somewhere between 1 and 2 seconds. And that's pretty reasonable for a lawn mowing. For lawn mowing, you get this thing started and then you're going as fast as you're going to go lawn mowing after about 1 point something seconds. It doesn't take long to accelerate a lawnmower to the speed that you want it at. And then you won't push as hard and you'll only be overcoming the friction. And at that constant velocity that you mow the lawn at for the rest of the time you mow the lawn is going to be maintained by the force that you add to it to overcome friction with no net force. So here we have which force is bigger. It's moving at a constant speed, right? Which force is bigger, force of friction or force of drag? So here they're kind of introducing us to something that we've not known yet, which we'll learn more about later. And that is that the reason that the car moves forward is because there's friction between the tires and the ground. As the tires rotate, they actually push backward on the ground, and the ground pushes the car forward. It's the same thing when you walk. When you walk, you push on the ground backwards, but the ground pushes you forward, right? You actually push backwards with your feet to move forward. We'll learn more about why that is. But they have the force of friction moving this car forward at a constant velocity of 10 meters per second, and drag pushing backwards. So which one of these forces is bigger?
Friction. I know they're equal, aren't they?
So are they equal or are they different? What does Newton's law say? It says force equals mass times acceleration. And we have a constant velocity, which implies that our acceleration equals
0.
0. If our acceleration equals 0, then this entire side of the equation equals 0. And that means that this is equal to 0. That means that this plus this must equal 0. And if they're going to equal 0, they must be equal and opposite, equal in magnitude, in other words, right? So they actually are equal, but except by a sign, equal and opposite to each other. Now, in the second scenario, we actually have some acceleration. So here's some acceleration. 10 meters per second forward. Which one of these is greater, the friction force that's driving it forward or the drag force that's pushing it backwards?
The friction force.
Yeah, because force still equals mass times acceleration. And we happen to know that the acceleration, if this is the positive direction, we happen to know that the acceleration is in the positive direction. If the acceleration is positive, mass can only be positive, so the force must be positive, right? That means that the friction, which is the positive of these two forces, must be bigger if you're going to add them together to get a positive force, positive net force. Right. So that's Newton's second law. We'll come back on Friday and learn about Newton's third law, and we'll do a bunch more of examples. But this is enough information for you to get started on the homework and to get most of it done, if not all of it. The Newton's third law is the only thing that we're lacking in some examples that we'll do together on Friday. So once again, if you have any issues with the exam, concerns or problems, make sure that you email me as soon as possible so we can take care of those. And we will see everybody on Friday.
You have a good day.
Thank you, you too.
Oh, and also I'm sorry about being a little late to the meeting. I tried doing the exam earlier and I lost track of time and came in like 10, 20 minutes late.
The exam?
Yeah, I did. I did finish the exam just because I thought I would be able to finish it quick enough since I had like an hour between my last class and this one. But
I guess I'm not understanding what you're saying. Hold on just a second. Let me, I need to do a couple of things before I can discuss this really quick. I got to stop my recording and all that. But then we can discuss that.
See you Friday.
See you later.